Okay, this is Chapter 11, Solutions, Lesson 1. We'll cover 11.1 through 11.4 today. This is actually the second time I'm recording it, so all of the writing is already there. I'm just going to go through it again. In sections 11.1 through 11.4, we will cover solution composition, energies of solution formation, factors affecting solution formation, and vapor pressures of solutions. First, let's review some 4 basic vocabulary terms. The solute is the substance being dissolved. The solvent is the substance doing the dissolving. A solution is a mixture of solute and solvent, and the solubility is the maximum amount of solute and a given amount of solvent. Some of these formulas we've actually already worked with. We already have worked with molarity, moles of solute over liters of solution. We've worked with mass percent, but now we're going to work with mass percent of a solution. So it's just the mass of the solute over the total mass of the solution, which is the solute and the solvent combined. We're going to revisit mole fraction, the moles of A over the total moles. And we're adding a new one, molality, is the moles of solute over the kilograms of solvent. Okay, let's look at this first problem. I'm going to have to work through it with you again. I'll change the color ink that I'm using. The density of isopropyl alcohol, C3H7OH, is 0.785 grams per milliliter. A sample is made by mixing 20 grams of isopropyl alcohol with 40 grams of water. So they want us to find molarity, molality, mole fraction, and percent mass. Well, I started with percent mass first because that's pretty easy. That's right here. We just need the mass of the solute, which was 20 grams, over the mass of the solution, which was 20 plus 40. So 20 over 60 gave us 33.3% mass. Then I went and I started to do the mole fraction. Mole fraction is moles of A. So the mole fraction of A is equal to the moles of A over the total moles. So we had to find the moles of the isopropyl alcohol, the C3H7OH. My letters kind of got mumbled together. C3H7OH. Okay, and we had 20 grams of that. We have to convert that to moles, so we're going to divide by the gram formula mass, which is approximately 60, and that gives us 0.333 moles of C3H7OH. And then we also need the moles of water because we need to calculate the mole fraction over the total moles. We had 40 grams. 1 mole of water is approximately 18 grams, and that gave us 2.22 moles of water. So our mole fraction, our moles of A, or our mole fraction of isopropyl alcohol, moles of A over the total moles, gave us 0.13 for our mole fraction. Molality, remember, is moles over kilogram. So we have moles over kilograms of solvent. So this was our moles of solute, 0.333. We got that from over here. And our kilograms, we had 40 grams of water. 40 grams is 40 kilograms, 0.04 kilograms. So our molality is 8.33 moles per kilogram, or molal. And molarity. Molarity is moles over liters. However, they told us that the density of the isopropyl alcohol was 0.785. So if it's not a density of 1 like water is usually at standard temperature and pressure, we have to take that into consideration. So we had 0.333 moles of the isopropyl. 1 mole is approximately 60 grams, and the density was 0.785 grams per 1 milliliter. And then we had to change milliliters to liters, 1 liter here. So that's 0.076. All of our other units cancel out liters. So molarity is moles over liters. So 0.333 moles over 0.076 liters gave us 4.36 molar C3H7OH. Okay, problem 2. The molarity of concentrated ammonia is 14.8 molar. It has a density of 0.880 grams per milliliter, and here they're asking us to find molality, mole fraction, and percent mass, starting with molarity. So, first of all, basically if it has a density of 0.88 grams per milliliter, that's 880 grams of solution per liter that we're dealing with. So we need to find out how much of this 880 grams. So this is the total grams of total solution. We need to find out how much of that is ammonia. So 14.8 moles of ammonia over here, and we know that 1 mole has a mass of 17 grams. So 14.8 times 17 is 252 grams of ammonia. So if we subtract that from the total solution, as I did down here, 880 minus 255 gives us 628 grams of water. So from that we can very easily find our percent mass, our solute over our total solution. So 252 over 880 gives us a 28.6% by mass of ammonia. And the last thing we need to find is our mole fraction. So we already know our moles of ammonia were 14.8, but we need total moles, so we need moles of water. So 628 grams, and 1 mole is 18 grams. So that gives us 34.89 moles of water. So our mole fraction is 14.8 over 14.8 plus 34.89. And that gives us a mole fraction of 0.29. Okay, let's talk about the energy of making solutions. The heat of solution, the delta H of solution, is the energy change for making a solution. And there's a couple of steps that have to happen in order to calculate the overall delta H of solution. First we have to break apart the solute, then we have to break apart the solvent, and then we have to mix the solute and the solvent. So in order to break apart the solute, we have to overcome the attractive forces holding the solute together. So that delta H has to be greater than 0. And the same thing goes for the solvent. We have to overcome the attractive forces between the solvent particles, so that delta H has to be greater than 0. The mixing of the solvent and solute will depend on what it is you're mixing. Molecules can attract to each other if the delta H is large and negative. Molecules can't attract if the delta H is small and negative. This basically explains the rule like dissolves like. And I have another chart that will help us out in a moment. This is from your note packet. As you can see here, the solute, we're separating it. That's delta H1. The solvent has to be separated. That's delta H2. Then the solute and solvent can attract to one another and form the solution. That is our delta H3. So the overall delta H of the solution is the sum of delta H1, 2, and 3. The mixing solvent and solute. That is a repeat. So let's take a look at this graph. The size of the delta H3 determines whether a solution will form or not. Now, in this case, it's showing us two possibilities. The reactants, okay, so we have delta H1, the solute splitting apart, delta H2, the solvent splitting apart, and then the mixing of the solute and solvent gives us a delta H3. Now, let's say that the delta H3 stopped here at the first solution line. Then, basically the products would be higher than the reactants. Therefore, our delta H of the solution would be positive or endothermic. If the delta H3 of the solution, if it ended here, then our products of the solution would be lower than that of the reactants, and therefore our delta H of the solution would be negative, and our heat of solution, that process would be exothermic. Here's the book page from your notes. Here you can see that the energy of separated solute and solvent is less than the energy of the mixing of the solute and solvent, delta H3, giving us a net negative delta H of the solution and an exothermic process. In B, however, the energy of the separated solute and solvent is less than the delta H3, the heat of solution for the mixing of the solute and solvent, giving us a net positive delta H of solution, in which case this would be an endothermic process. Here you can see what happens when you mix various types of solute and solvents. Here, if you have a polar solvent and polar solute, you wind up with a very small delta H of solution overall, and the solution forms. Here you have a polar solvent and nonpolar solute. So your net result after breaking apart the solvent and the solute and then them trying to join is large and positive. Therefore, no solution forms. Here you have a nonpolar solvent and a nonpolar solute. Again, here you can see that your delta H1, 2, and 3 are all very large, small, and so your delta H of solution is also small. So a solution will form. And in the last one, you have a nonpolar solvent and polar solute, and again, you wind up with a net delta H that is large and positive, and therefore no solution forms. So you can also, this also helps us understand like dissolves like, because any time that we have a like polarity, we form a solution, and any time we don't, we won't. Types of solvent and solutes. So to sum it up, if a delta H of solution is small and positive, a solution will still form because of entropy. There are many more ways for them to become mixed than there is for them to stay separate. Like dissolves like, which means polar dissolves polar and ionic, and nonpolar dissolves nonpolar. Polar will not dissolve nonpolar. Again, let's just briefly review our polar, our Lewis diagrams to understand this. Here we have water, which is polar. The oxygen side is slightly negative due to a higher electronegativity than the hydrogen side. And when that comes in contact with hydrochloric acid, so say I'm diluting concentrated hydrochloric acid in water, Hydrochloric acid is also polar, and therefore there will be some hydrogen bonding taking place between the oxygen of the water and the hydrogen of the hydrochloric acid. Nonpolar and polar. Here again is my polar water, okay, and a nonpolar molecule. There's no attractive force here. The oxygen is negative, okay, but there's no charge on the methane because it is symmetrical and there's an equal distribution of charge. Nonpolar, remember, relies on London dispersion forces, and electrons are constantly moving, and therefore there is a temporary induced dipole and a very, very weak force there between the molecules. Structure and solubility. Water-soluble molecules must have dipole moments, polar bonds. To be soluble in a nonpolar solvent, the molecules must be nonpolar. A good example of this is on page 492 in Zoomdal. So if you get a chance, read the vitamin A, vitamin C discussion. Another good example is soap. Soap has a hydrophobic end, or nonpolar end. Hydrophobic meaning phobic, fear of water. And it also has a hydrophilic end, meaning friend of water. So you can see that you have a nonpolar spine with a polar end, which becomes very useful. If you have a drop of grease in water, grease is nonpolar, water is polar, they will not mix. The soap lets you dissolve the nonpolar in the polar because it acts as a bridge. The hydrophobic ends dissolve in the grease. So here are your nonpolar tails that dissolve in the grease because the grease is nonpolar, with your hydrophilic heads sticking out of the grease drop. Along comes water, and the hydrophilic ends, the red heads here, dissolve in the water. The water molecules can then surround and dissolve the grease. Helps get grease out of your way. Let's talk about pressure effects. Changing the pressure doesn't affect the amount of solid or liquid that dissolves. They are incompressible. That's really important. Pressure only affects gases. Pressure affects the amount of gas that can dissolve in a liquid. For example, mineral water or soda. The dissolved gas is at equilibrium with the gas above the liquid. The gas is at equilibrium with dissolved gas in the solution. The equilibrium is dynamic. So here's a closed container, and there's an equilibrium between the gas above the liquid and the gas below the liquid. However, if I change the pressure and I increase the pressure of the gas molecules, they dissolve faster. Why? You're decreasing the volume, you're increasing collisions, the equilibrium is disturbed. The new system reaches a new equilibrium with more gas being dissolved due to the increase in pressure. This is actually Henry's law, which states that the pressure is equal to a constant times the concentration of gas. Increased temperature increases the rate at which a solid dissolves. We can't predict whether it will increase the amount of solid that dissolves. That we have to determine from a graph. So increased temperature, just like increasing the surface area, will increase the rate at which something dissolves. In order to determine if it will actually dissolve more, we read from a graph. So we have two different cases. One, solid dissolved in a liquid. So generally, the higher the temperature, the greater the solubility for solids. For gases, however, the higher the temperature, the lower the solubility. Because if you heat a gas, the gas molecules want to spread out. They're not going to want to go into a liquid. These two charts show you the solubilities of solids and gases. On the left, you can see that generally the solubility of a solid increases as temperature increases, with the exception of sodium sulfate and cerium sulfate. On the right, you can see, generally speaking, that as you increase temperature, the solubility of a gas decreases. Therefore, the higher the pressure, the more gas that can dissolve in a liquid, which is Henry's law. A good example of what we're talking about has to do with thermal pollution as well. In the United States, there are laws that regulate thermal pollution, but this is not worldwide. For example, a factory can pull cold water out of a lake or a stream in order to use in the manufacturing process. In countries without regulations, that water is then dumped, now warm because it's been used, back into that same body of water. This decreases the amount of dissolved oxygen that is in the water, because as temperature increases, the solubility of a gas decreases. This then suffocates the fish that don't have enough oxygen, decreases the fish population, and ultimately alters the food web. In this country, we have regulations that prohibit this, and we have what's called a cooling pond, in which the warm water is not released directly from the factory into the body of water from which it came. It goes into a cooling pond that has bubble stones, and it cools the water before it is put back into the natural habitat. So gases are pretty predictable. As temperature increases, solubility decreases, and gas molecules can move fast enough to escape. And a good example of this, as you just saw, is thermal pollution. The last thing that we need to discuss is vapor pressure of solutions. A non-volatile solvent lowers the vapor pressure of the solution. So for example, salt in water. The molecules of the solvent must overcome the force of both the other solvent molecules and the solute molecules. So in this example that we have here, we have pure water and we have an aqueous solution under a bell jar. After a period of time, all of the water is transferred to the aqueous solution. This is because the dissolved non-volatile solute decreases the number of solute molecules per unit volume, and it should proportionally lower the escaping tendency of the solvent molecules. Why does this happen? Because solutions have lower vapor pressures than pure solvents. This diagram can be better explained in these three subsequent slides. Here, water has a higher vapor pressure than the solution. Therefore, the water will evaporate from the water. Water evaporates faster from the water than from the solution. So the water is evaporating faster than the aqueous solution, and therefore all of the water condenses faster in the solution, and that's where it winds up. Okay, the last thing we need to discuss is Raoult's law, which says that the pressure of a solution is equal to the mole fraction of the solvent times the pressure of the solvent. Two very easy things that you know how to calculate. It applies only to ideal solutions where the solute does not contribute to the vapor pressure. So that's really important. We're not going to worry about the solute here because we're talking about an ideal solution. Again, this just shows you the red lines here are water, and the blue lines have to do with what happens when I add a non-volatile solute, say like salt. Note that the boiling point of the solution is higher than that of pure water, and conversely the freezing point of the solution is lower than that of pure water. This shows the effect of the non-volatile solute on the solvent and how it extends the range of that pure substance. So here's the boiling point of water. I add salt. Here's the boiling point of water. Here's the freezing point of water. I add salt. Here's the freezing point of water. Now again, depending on what salt I add, that will determine how far the boiling and the freezing point changes, which is in the next lesson. So let's calculate these last two problems and we'll call it a night. What is the vapor pressure of a solution that contains 155 grams of table sugar dissolved into 100 grams of water at 25 degrees Celsius? The vapor pressure of the water at 25 degrees is 23.76 torr. Now, we're not interested in the table sugar. What we're interested in is the mole fraction of the water, the solvent. But in order to calculate the mole fraction of the solvent, we need to calculate the moles of sugar that are involved here. So I had 155 grams, 1 mole equals 342 grams, which gives me a mole fraction of 0.45. I have 100 grams of water, 1 mole is 18 grams. That gives me a mole fraction of 5.56. So my mole fraction of the water is equal to 5.56 divided by 5.56 plus 0.45, which gives me a mole fraction of 0.924. Therefore, the pressure of the solution is 0.924 times 23.76, or 21.9 torr. Not so bad. And the last problem. A solution is prepared by mixing 5.8 grams of acetone and 11.9 grams of chloroform. At 35 degrees, the vapor pressure of pure acetone and chloroform are 345 and 293 torr respectively. What's the total vapor pressure? So we have this, we have this. What I had to find was the mole fraction. So what I did was A for acetone, 5.81 grams, divided by the GFM of 58.1, gave me a mole fraction of 0.1. 11.9 grams of chloroform divided by 119.4 gave me 0.0996 for moles. So my mole fraction of acetone, 0.1 over 0.1 plus 0.996 gave me 0.5. And for my chloroform, 0.0996 divided by 0.1 plus 0.0996, 0.5. Which gave me 0.5 times 343 plus 0.5 times 293, 319 torr. That concludes Lesson 1, Sections 11.1 to 11.4.